So yeah, my backup slides are just 200 holiday photos. So fortunately, they are working. So yeah, I'm Ada Rose Cannon. I'm a developer advocate for Samsung. Tech-wise, my interests usually lie in like front-end, real-time graphics stuff. I do a lot of stuff with WebGL and virtual reality in the web. That's not what I'm talking about today. Today I'm talking about like making your regular like CSS and HTML and DOM websites work really fast. So yeah, I work for Samsung Internet. Has anyone here heard of us before? A few. This is pretty good. This is better than what we normally get. I'm being honest here. Okay, who here tests in our browser? Ah, I am disappointed. I'm walking off right now. No, I'm kidding. Right. So all those who raised your hands, and actually you didn't, all you've heard of Samsung Internet, please test in our browser. We're a fork of Chrome. We're not just like a wrapper around like the native web view. We're like an actual browser. There will be some differences because although we try for perfect browser compat, like nobody's perfect. So we try as best we can. So please test your websites in our web browser and report bugs back to us. So that's the bit I get paid for. Now onto the good stuff. Cool, so I'm talking today about web workers. And not just like a high level, oh, web workers are really cool. They are, and we all know this, web workers are cool. But like how to get them integrated into your app if you haven't already been using web workers. Is anyone here using web workers in their product already? One or two hands? What about service workers? Okay, same hands. I'm not talking about service workers here, but it's another type of web worker. Similar rules apply. So yeah, I was building an app a while ago, and I saw this amazing CSS filter, which would make your web page go really blobby. So you could like bring two elements close together and they would like suck together. It was really cool, and it was really powerful, and it basically involved importing an SVG filter into CSS. Unfortunately, it meant anytime anything caused a repaint on your page, it would have to repaint the entire page. But it was worth it. It looks really cool. And because it had this cool blobby effect, I wanted to hook it up with some real-time physics. So I hooked up a like a Valet-based physics engine to it. And if you haven't done much physics engine-y stuff before, like if you find a basic Valet engine, so VERLET, it's a great place to start. You can do really cool interactive stuff in your pages. If I'm building anything, I'll just throw a physics engine in there just to make it fun and like fun to play with, because like why make boring websites, right? But by doing this, I'm nailing my CPU with JavaScript as hard as I can to do the physics engine, because I've got like up to 1,000 physics points running at the same time with like twice as many constraints running for all these like strings and stuff connecting all the bits. I'm also repainting the page every single time anything moves, and because it's a physics engine, everything is moving all the time. And if you repaint in the browser, that's done on the CPU. Like it's not done in the graphics card. Like the paints are done on the processor, then they're sent to the graphics card for compositing. So I'm like hitting the CPU as hard as I can. So obviously I pick the lightest possible front-end framework I can. So in this example, I'm using HyperHTML, which is super light. It's only like a few kilobytes in size, but it's also incredibly fast and really lightweight. So that works really well for that. But even though my front-end framework is so light, on laptops which have any kind of high DPI screens, the frame rate just plummets as the CPU just starts taking off and the fans are going wild and my phone is burning my hands. So I'm like, okay, I love this effect and it's really good, but I can't just be delivering this experience to like people with great phones. So I started to look at web workers to try and solve this issue and started moving stuff into a different thread. But before I get into like how I got into that, I'm going to make sure we're all on the same page with with a lot of the language I'm going to be using in this talk. Because if you're dealing with web workers, you're dealing with asynchronous code. So stuff is not going to be happening in the right order. And the web's been dealing with asynchronous stuff for a while, and in many different ways. So back at the beginning, the way it dealt with asynchronous stuff is that it didn't. Everything was synchronous. So here we're making an XHR request, and we're fetching some data, and we're doing some stuff with it. But what the page will do, it will block the main thread until it's downloaded, so nothing will happen. So you know, like when you open like an alert window and the whole page freezes? It will do that. But back then it was fine because people weren't really doing XHR all that much, and people weren't really expecting, weren't building the same like smooth app experiences we're building today. I mean, this is 90s, I think, like late 90s, slightly before my time, although not by much. Don't want to give away how old I am here. But yeah, it got better. So XHR gained the ability to have an event listener. So you can make a request and wait for the load event to happen, and then respond with the data you get and do something. So now for the first time in JavaScript, we're writing code which doesn't happen in the order it's written. So it'll go down until it gets this event listener, and then it'll save your function for when the I/O is finished. This is cool, and it's start of a long history of I/O in the web. So get user media. So this isn't waiting on some kind of I/O event like fetch or local storage. Actually, local storage is an interesting one. So local storage is an I/O event in the web. So I/O, like in-out, reading a hard drive. But unlike most languages where you do something that accesses the hard drive, it's not actually asynchronous, it's synchronous. That's why there's like a long, that's why it can be slow if you do many read-writes to local storage. So it's often encouraged now to use one of the various database, web database solutions for accessing hard drive data. So the other way of doing callbacks in the web was not in the web at all. This is Node. Who here programs in Node? A few people? Cool. So Node had its own way of doing callbacks. So instead of doing a callback for it succeeded or it failed, you have one callback with different parameters for whether it failed or succeeded, respectively. This worked. This was really popular for a long time, and then 2014-ish, like lots of libraries started to include this thing at the time, which was new and weird, called promises, and promises were really cool. And shortly after that, when ES 2015 started landing in browsers, we got it in ES 2015 as well, and we could use it for all kinds of stuff. So here's how we use it in fetch. So it's like fetch something, and then you have .then to wait for the response to finish. And you can chain them, and you can do lots of nice stuff, and it makes your code look really very neat. And nowadays, all new web APIs, if they do anything that's asynchronous, whether it's waiting for permission or getting something from network or from disk, it's usually going to be based around promises. And the reason is not because this API in itself is particularly nice, but because it enables this one. So this is Async Await. Async Await allows you to write asynchronous data using our common, old-fashioned, like bog standard synchronous control flow. So you can use for loops for asynchronous stuff, which is really cool. So you can await a promise in an async function, And what it will do, it will essentially pause that function and start doing other stuff. So although it looks synchronous, like in the very first example, this doesn't block the thread. The thread can carry on doing other stuff and being nice and busy when you're waiting for your promise to resolve, which is really nice. So who here is using Async Await at the moment? A fair few hands. Who here is shipping Async Await to clients, like to browsers, without transpiling it? Good. Oh, 2. Yes. Yeah. Oh, web, is that all? Okay. Okay. Is anyone doing like multiple targeted transpiles? So you're sending like the transpiled crap to like bad browsers and like the real good modern stuff to other browsers. So a few of you, and you're shipping Async Await? This stuff is so cool. It makes the code look so neat and good. Start using it. Like, use the new shit. If you don't use it, like, why add? The browsers won't add more stuff. Sorry, I like web technology. Anyway, yeah. So all the stuff I talked about just now, this is like asynchronous programming. But it's asynchronous, but it's not parallel. So what I mean by this is that, like, yeah, it can swap around and run bits of code out of order, but it all happens in the same timeline. So if one of those lines took a really long time to happen, everything else would have to wait for that to finish before it could carry on. So you end up with this threads where essentially stuff appears to be running at the same time, but it's not. It's just like the operating system's pretty good at shuffling stuff in so it can run code out of order and make the most of the processing power that's available. But this threaded model, so this threaded model kind of goes back to like a long time. Like this is part of like the fundamental processing model for computers, where you have a CPU that can do some calculations, and you have a chunk of RAM where you can store instructions and other bits of information you want to store in the RAM. I'm not going to go into all the details because I haven't got time to run over like an operating systems course with everyone. But keep it simple. You have a CPU that does calculations, and you have a RAM where you can store stuff. And this worked really well. It even and even in modern operating systems, when you have like even if you have a single processor, you can still run multiple threads at once, but they don't know how many processors there are. I mean, they can look, but I mean, like instinctively, they don't know. As far as they're concerned, there is one CPU, and they have one chunk of RAM, and that's what they deal with. And it doesn't matter how many of these there are, the operating system will fake it. So they can think they have oodles and oodles of RAM when you only have 128 kilobytes of it, because it can like page stuff off to the hard drive. Or it can think or it can run many programs even though you have a single CPU. This worked really, really well for many years because computers were getting more and more powerful, getting more and more transistors onto a single chip. And so for a while, you could quite reliably say, yeah, I might have a processor with only 1 or 2 cores, but if I buy a core in 18 months, it's probably going to be twice as powerful. It's going to go up from 1 gigahertz to a whopping 2 gigahertz core. And yeah, Moore's law still applies, but the model Moore's law is happening in has changed. So this is, oh shoot, I left my phone down there. I was going to show you, this is the chipset on my phone, which is kind of a weird one, because this is 2 very powerful cores, 2 medium powerful cores, and 4 tiny little ones. And you don't know where your browser is running, or where it's like running from. As far as you know, you could be running on one of those tiny cores. Or you could be running on the big beefy ones. But to be honest, that doesn't really matter. You shouldn't be expecting to run on one of the big beefy cores anyway, because there are many reasons why a phone won't be using it. If you're in power saving mode, it probably won't be using like the best hardware in the phone in order to save battery power. Because if it was firing on both those custom CPUs at the same time with all the graphics chip running, like your phone would be melting your hand. It would be burning a hole in your back pocket. You'd have a battery life of 45 minutes. Like it doesn't do that. Those were arbitrary numbers. I can't speak for statistics of Samsung phones. Yeah, so, but phones themselves are getting more and more to this architecture, like of having many low-powered CPUs. And the median phone isn't getting better. Like the median phone is becoming a cheaper phone as time goes on, as more people come online and start buying their first smartphones. I'm totally stealing this from Alex Russell, but because he likes to talk about this. And if you should see his talk about chipset manufacturing, it's amazing. But factories keep producing phones with really old chipsets, because chipsets are really expensive to produce, and once you've got a factory that can produce them, you might as well just keep printing them. So the median phone is getting worse, and it might have a few cores, but they're not going to be powerful. In addition, like these threads running on these cores, it already has huge amounts of responsibilities, which are more important than the code you're writing. I'm sorry if that hurts as developers. But passing the HTML and the CSS gets higher priority than your JavaScript. Then it runs your JavaScript. It then lays out the page and paints the layers. And it might have to do this multiple times per frame if your JavaScript is doing something really bad. And as time goes on, like our JavaScript is getting bigger, and bigger, and bigger. And it's not getting better because, who here has an iPhone? Who here has a Samsung phone? Okay, that's not as many. But who has a top-of-the-line phone in general? Most of you. And you're building apps to run on your phones, which are really pretty good, but they're not the devices most people are using. And if your JavaScript gets too big, you'll get kind of thing. Dan, could you push the top button? So here sorry, my laptop's over there, that's why I'm delegating to Dan. So if you're doing a lot of CPU operations, oh shit, I actually break the page. I love it. Oh, that's really quick. Yoav, your laptop is really powerful. On my laptop, this takes 5 times longer. So I just calculated 30,000 digits of pi on the main thread, as you do. I know it's really stupid, essentially trying to crash the browser in the middle of my talk, which runs out the browser. But yeah, as you saw, do you want to press it again, Dan? So as you saw, whilst it was running the CPU, the Pi stopped spinning. And it's because the browser is putting all of its CPU power into generating these stupid numbers, rather than well, I mean, they're not actually for anything. You need 30,000 digits of pi, then you're trying to calculate the radius of the universe down to an atom. You need 1. Sorry, I'm a physicist. Pi is 3. Yeah. Could you go on to the next slide? So yeah, whilst you're calculating those numbers, the page stops. And in normal apps, this usually manifests as jank. So you're doing something really stupid with your JavaScript, and you've blown your frame budget, which is about 16 milliseconds on a 68 frames per second device. and it skips. And that's really annoying. But then you do that 2 or 3 times in a second, you're really going to piss off your users. They're going to be like, this is why the web is terrible. I should download an app. And then they will stop using the web, and then we'll stop getting funding. And then no one builds web browsers anymore, and then the web disappears. So yeah, if you're timed to like do JavaScript or paint something, like my example at the beginning where I had that totally nuts CSS filter is usually not the reason most people are having jank, because CSS is extremely fast and browsers have got really, really good at laying out pages efficiently. Usually it's some stupid thing happening in the JavaScript, like you're laying out the page and then reading from that layout and then laying it out again, and then you're doing that like 10 times in a row and making stuff repaint or relay out. Yeah, so it's usually caused by JavaScript. This is where I had a couple of slides saying, this is your fault, you shouldn't do it, but I got rid of those because I thought you'd be really mad. So yeah, we can take advantage of multiple threads in the web to run our JavaScript. So Dan, could you push the second button, please? So here I'm calculating pi in a web worker. Yay, web workers. Now I'm getting to like the good shit. Sorry, I shouldn't swear. I'm on live stream. So yeah, the pi kept spinning because the CPU was like being used up in a different thread. Then when it was done, it sent the answer, these 30,000 digits of pi, back to the main thread, where it then displayed them. Oh yeah, could you go on to the next slide, please? Cool, so this is how you usually load a web worker. You go, my worker, new worker, some JavaScript file. That's cool in the way you do things. Actually, funny thing with web workers. So web workers can't yet do ES module imports. Actually, who is using like ECMAScript imports, like JavaScript imports? A few of you. Use them, they're really cool. Stop using all that common JS crap. Use like standard stuff. Sorry, I like web tech. Yeah, imports are really cool. If you can use them natively in the browser, they're really well supported, and they're kind of rad and fun, and I use them for everything, including this slide deck, which I'm really proud of. So yeah. So although I've just told you, yeah, you don't bundle, use ES module imports, unfortunately with web workers, you still have to because imports aren't supported there yet. You can still use like import script. You may have used it before in service workers and stuff to bring stuff in, but that usually like doesn't fit in with whatever like module loading system you've got set up. But who here already has a humongous build system set up for their app? Be honest. Yeah. Like, yeah, you can use your humongous build system to just knock out a bundled together worker file. The other option is to assemble it yourself, like on the fly in JavaScript. And this works. This is actually like kind of a fun hack. You can generate a JavaScript blob, create a URL for it, and then you can use that and load it in as your web worker. I've done all kinds of stuff like importing files from node modules and just like chopping the bottoms off, top and bottom off, just so you get the actual JavaScript code, and splicing them together like that to build web workers. It's really dirty, but it actually works, pretty fun. Don't do it, but it's kind of fun. I mean, it's like really flaky because you're basically going, get rid of the top 5 lines and the bottom like 6 lines, and then just take that middle bit and then like import the dependencies. Yeah, don't do it. So yeah, web workers are really cool. They let you spin pies whilst calculating pi. Yay! But they do have some limits. So like I said earlier, you can't pick the CPU to use. You could land on one of those tiny CPUs, which like the phone's reserving for like not very important stuff. Or you could even land on the same CPU you initiated it from. The operating system will pick whatever CPU to use, depending on its own heuristics. You can't access the DOM. It's in a different thread, which means like it's separated in memory. So you can't access the DOM. You can't share any kind of JavaScript state. Like you can't have one object they can both access. I mean, yeah, there's shared array buffers, but they kind of got a little bit deprecated in some browsers, well, in all browsers due to Spectre, and there was timing attacks. But I think they're being re-implemented, but they're not everywhere yet. But keep an eye on them, they're really cool. And you can't access some of the device resources like cameras and microphones and stuff like that, because that'd be pretty creepy if a background process could access those. But you can use stuff like off-screen canvas and other things to do stuff. Basically anything involving calculation, move it off to a worker if you can. And because it is like an actual like computer thread, it's not just like some fake thing where it's running some stuff separately. No, it's actually spinning up another thread on the computer. Like it has its own CPU, it has its own RAM. Like as much as you can like access these in details using JavaScript and stuff. So your main thread will have your DOM, your style sheets, like it'll have some JavaScript you're running, and there'll be some kind of like state. You'll probably also have some kind of representation of that state which you've tried to keep synced in your web worker, and your web worker can also run some JavaScript. But like, what's the point of having a web worker if it can't actually access the DOM, if it can't do anything that the user's gonna see? So I'm borrowing someone else's laptop. This is an ASCII arrow that's going back and forth. They said you get some tofu instead. But tofu's like for when you get like a rectangle for when stuff doesn't load. Yeah, so you can send information back and forth between threads using post message. So like I can send a message, so I can like post message an object to the main thread. And in the main thread, I can listen for that message, and I can log something to the console. And it kind of happens like this. So I want to send this message, and then the browser will serialize it into some like string or some magic method that's hidden behind the scenes in the browser, and it will reconstruct that object in the main thread. So there are now two of them in memory, one in your web worker, one in your main thread. If you change it in your main thread, the changes won't be reflected in the web worker. They're different objects. But some objects can be sent back and forth. So array buffers, which are which represent chunks of memory in JavaScript. You can send message ports, which allow you to reply back along web workers. You can generate image bitmaps using off-screen canvas and send them too. But array buffer is what you're going to use mostly. So in this example, I'm going to transfer this array buffer to the main thread, which is that buffer at the bottom. So when I send it across, the browser will serialize the object again into some, however it serializes it. It's behind the scenes. It's opaque. We don't know what it is. And it goes back into the main thread. But what happens is that the original buffer is now inert. If you try to use it, you'll get an error. Because the memory that was allocated for that array buffer has now been allocated to the main thread instead. So it hasn't copied it and rewritten it. It's just changed the ownership of like some chunk of RAM, which is super cool because you can transfer something like megabytes large of RAM to one thread to another very efficiently. Whereas if you were to send a very large object, it would have to serialize it, and then you have to reconstruct it again in the main thread, which can be very slow, especially if you want to do something multiple times a frame. What do I want to talk about here? So yeah, this is usually the way we want to do stuff with workers. You want to send some message, you want to get something back, and then go, ah, great. And then we'll send something back and do that, and you get back. And you usually want this like back and forth where you're doing stuff. But this isn't the way usually things work in reality. Because often you might not get a response for a while, and then you might get a couple back, and you might try working on stuff, but you can't tell like what's a response to what. The order is largely opaque, and you can do weird stuff to keep track on it, like generate unique IDs for every message you sent and match it up. It's a real pain in the ass. Like workers are really old. Like they were made for this post-message architecture, which, if you remember from my earlier slides, like post-message was like one of the really early ones which were introduced into the web, like receiving messages with event listeners. And it's not ideal for like modern. Am I low on time? All right, cool. So yeah, post-message architecture is like not ideal because you have to refactor your app to constantly be waiting for stuff to arrive and then send stuff across again. So you can't just dump it into your app and have it work. Like you can't get stuff matched up. Syncing state is a real pain in the ass because if you're not sure when stuff is coming back and how long it's going to be, it's hard to guarantee that the state you think you have in your web worker is the state you have and that it matches up with the state in your main thread. It's hard to force this serial back and forth. But Comlink. So this is the thing which I really wanted you to take away from this talk. Comlink is an amazing library. It was written by Zoma from Google, and it essentially wraps web workers letting you like proxy classes and functions from your web worker or your main thread into the other one. So you can write code that looks like normal JavaScript and treat it as such, and by adding and it returns promises for all the methods. So you can await those promises. So for example, if I have this library where I'm doing some stupid maths, where I'm going math.add 2 + 2 and 3 + 7, I can port this to a web worker. And then if I wanted to use it with a web worker, all I have to do is wrap it with Comlink, and then I can await for each function to return a result. So here I'm going, please create a new instance, and then it returns me the proxied one. I need to stop. I'm out of time. Oh, shoot. OK. I'm going to end it there because Comlink is really cool, and shame I'm missing all the really good shit. All right, cool. Yeah. So I've been Ada. Sorry about that. I'll put the slides up later so you can see them.